Now let's turn to the task of actually implementing collaborative filtering and look at the complexity of the implementation. The most expensive step in implementing collaborative filtering is the step of finding the k most similar users or the k most similar items, the neighborhood of an item or a user. Remember, what we had to do to find the k most similar item was to take the item and compute its similarity with respect to every other item. And this required us to compute, for example, a cosine or a centered cosine distance between the item of interest and every other item. If we actually did this at every step, we'd have to actually look at every entry in the utility matrix. And so the complexity of doing that turns out to be the size of the utility matrix U. Now, since the utility matrix can be really, really large because there are many, many users, millions of users and millions of items, clearly it's impractical to do this at runtime. So what we really have to do is to pre-compute. Pre-compute for every item the set of other similar items, or for every user the set of similar users. But even a naive pre-computation can take a really long time. Suppose there are n items and we are doing item-to-item collaborative filtering. For each item, we'd have to compute its similarity to every other item. And so the complexity of doing that is a product of the number of items and the size of the utility matrix. Now, since the utility matrix can be really large and the number of items can be really large, the product of these two is clearly a very large number. And so even a naive pre-computation can be too expensive to do in practice. So how do we deal with this? Now, in previous lectures, we looked at a way of doing this. And that technique, those are the techniques for near neighbor search in high dimensions. For example, locality-sensitive hashing. We can use something like LSH to take an item and quickly find a set of near neighbors to that item, or take a user and find a set of near neighbors to that user, and do that in advance. In practice, you might do something like this, once in a day, for example, or once every few hours. We can also use clustering to group users and items into smaller clusters, and thereby speed up the process by restricting the search to within a cluster as opposed to in the entire set of items or users. And finally, we can use a set of techniques called dimensionality reduction methods, which we'll cover in an upcoming lecture. What are the advantages and disadvantages of collaborative filtering? The biggest advantage of collaborative filtering is that it works for any kind of item. It doesn't matter whether the item is books or music or videos or news articles or people. Collaborative filtering just works for any kind of item without requiring any feature selection, which is actually the biggest advantage of collaborative filtering, because it turns out to be a really tough problem to find the right set of features for something as complicated as a movie or a piece of music. And it sort of also explains the huge popularity of collaborative filtering, because it sort of obviates this need for feature selection for complex things such as images and movies and music and so on. That said, collaborative filtering also has a number of disadvantages. The first of these is cold start. For collaborative filtering to work, you need enough users in the system who have rated enough items. Remember, we need to, given an item, we have to find a set of other similar items, or given a user, we have to find a set of other similar users. But if there are not enough users in the system, it's hard to find a match. The second problem is one of sparsity. Even when we do have enough users in the system, because there are so many items, typically there are millions of users and millions of items. Most users have not rated most items, and therefore the user ratings matrix is very, very sparse indeed. And it's hard to find a pair of users who have actually rated the same set of items. Right? So remember, suppose I wanted to predict the rating for a user X and an item I need to find other users who also rated item I. It might be really hard to find such a set of users because of sparsity. The next problem is the first rater problem. Suppose we add a new item to the catalog, right? You cannot recommend this new item to anybody because the new item doesn't have any ratings. And esoteric items, for instance, that are actually, there may be a few people who really love the item, but the number of people who like the item is really small, tend to have a smaller number of ratings, and it's hard to make recommendations for those items too. And the final problem of collaborative filtering is that it tends to have a popularity bias. Let's take a really popular movie or book like Harry Potter. Now, lots of people tend to give high ratings to such a popular book or movie. And collaborative filtering will therefore tend to recommend a popular book or movie to almost everyone in the system, regardless of whether they'd actually like it or not, just because the neighborhood of any item will include popular items. At Amazon, we used to call this problem the Harry Potter effect. And the Harry Potter effect need not be a bad thing. Recommending popular items generally works out well. But it's, the problem is if every item that's recommended is a popular item, the popular items can completely crowd out the unique recommendations that can be made for a specific user. And you have to take special steps to avoid the popularity bias from washing out the specific recommendations. Now that we've seen some of the difficulties with collaborative filtering, we can design hybrid methods to overcome those difficulties. For example, we can add content-based methods to collaborative filtering. We can add item profiles to deal with the new item problem and make recommendations of new items to users. Or we might take new users and use demographic information about new users to build synthetic profiles for them and thus deal with the new user problem. Another approach is to implement two or more different recommender systems and combine their predictions, perhaps using the linear model. For example, you could use a global baseline recommender and combine that with collaborative filtering. And let's see how to do this. So here's a problem. We'd like to estimate Joe's rating for the movie The Sixth Sense. The problem is that Joe has not rated any movie similar to The Sixth Sense, according to our measure of similarity. And so using the collaborative filtering formula that we saw in the previous slides, we can make no prediction for Joe's rating for the movie The Sixth Sense. This is a problem that arises from the sparsity of the rating matrix. So here's an approach called the global baseline approach. And it's actually very, very simple. Suppose in our system, the mean movie rating is 3.7 stars. 3.7 is the average rating for across all movies and all users. And we observe that The Sixth Sense, the average rating for Sixth Sense is 0.5 stars above the mean movie rating. People like The Sixth Sense on average more than the average movie. We also notice that Joe rates 0.2 stars below the average rating for other users, right? This is not Joe's rating for The Sixth Sense or for any specific movie, but if you take the average of Joe's rating, Joe turns out to be a tough rater, and his average rating is 3.5 stars as opposed to the mean rating of 3.7 stars. And so Joe's rating in general are 0.2 stars below average. Now we can use these three numbers to come up with the baseline estimate for the user Joe and the movie Sixth Sense. We start with the mean rating, which is 3.7. Notice that the Sixth Sense is 0.5 stars above average, and then we subtract the 0.2 because Joe's rating is on average 0.2 stars below the average rating, and we predict that Joe will give the Sixth Sense 4 stars. Notice that in this case, we have not used any specific information about the movies Joe has rated, or we don't need Joe to have rated any movie similar to Sixth Sense in order to make this prediction. All we need is to have enough users and who have actually rated the Sixth Sense, so that we can actually compute an average rating for the Sixth Sense. Now what we'd like to do is actually combine this global baseline rating with collaborative filtering. So let's look at an example. So the global baseline estimated that Joe will give the Sixth Sense 4 stars. Now, suppose we use a collaborative filtering, a nearest neighbor approach, and we actually find out that Joe didn't like the movie Signs, Signs actually happens to be a movie that's very similar to The Sixth Sense. It's actually by the same director. And let's say the similarity between Signs and Sixth Sense is 1.0. We find out that Joe didn't like Signs, and in fact, Joe rated Signs 1 star below his average rating for all movies. So now we can combine the global baseline estimate and the collaborative filtering refinement and come up with the final estimate. So since the global baseline estimates that Joe will rate The Sixth Sense 4 stars, whereas the collaborative filtering gives it a -1 below his average rating, so we can just add those two ratings and predict that Joe will rate The Sixth Sense 3 stars. So notice that this approach actually takes a linear combination of two independent classifiers, a global baseline classifier and the collaborative filtering classifier, and takes the sum of those, it takes the sum of those predictions. And if we wanted, we could have weighted these predictions in different ways as well. In this case, we weighted both of those equally. So finally, here's the formula that you can use to implement the combination between the global baseline and collaborative filtering. Let's define Sij to be the similarity of items I and j. And given an item I, we are going to find its k nearest neighbors. And we are only going to find the k nearest neighbors that have also been rated by user X. And our goal is to estimate the rating for user X and item I. And above here, I've given the simpler formula that we had, which was just a weighted average rating for all the items in the neighborhood NIX. Now we're going to add in the global baseline idea, and here's what the new formula looks like. We're going to estimate the rating Rxi to be the sum of a baseline rating and the collaborative filtering refinement. Bxi here is the baseline estimate, and the baseline estimate for user X and item I is itself the sum of three components. Mu, which is the overall mean movie rating in the system. Bx, which is the rating deviation of user X, which is just the average rating that user X gives across all movies that he has rated minus mu. And Bi is similarly the rating deviation of movie I. And so if you add those three up, you get Bxi, which is a baseline rating for user X and item I. And then we are going to add in the collaborative filtering piece, which is the same as the formula we had before with the weighted average, weighted by similarity of item I and item j in the neighborhood. However, instead of using Rxj, which is the rating of user X for item j, we're just going to subtract out the baseline piece and only look at the deviation in the rating for the item from the baseline. Since we've already added the baseline piece, we don't want to double count it in the second piece here as well. So we subtracted out the baseline ratings from the collaborative filtering piece. And this gives us the final formula that combines collaborative filtering and the baseline approach.